And so we started out with a little on the network, and it was a great deal of fun to think back and hear some of the origins of where some of the thinking was, and to have a chance to discuss exactly where we are in the evolution of this. Either it's the Internet of Things, or according to Steve, it's things on the Internet, whichever we decide it is. But we're going to move right into tags, and we have the director of the Auto ID labs at Fudan University in Shanghai, Professor Hao Min, who will start off the session.
Okay, and you know, the whole RFID technology, I think it's the first thing starting is from the RFID tag. So every people thinking about the tag, and what the performance of the cost of the RFID tag may just influence the adoption of this technology, because it's kind of like the basis for this whole technology. So today I will talk about what's the user requirement for tags right now. And so this will promote us to research on what the next generation we can do for the tag performance enhancement. And also, I will introduce some new technologies being developed right now. There are already some adoptions of this RFID technology. Some users are used as tags. There's it's estimated that millions of tags be used right now. But there are still some problems. People want a longer read range. Right now, a UHF tag can reach the range as approximately like 5 meters. But people are thinking about whether we need like 10 meters. If you reach 10 meters, more application will be wider. The another thing is really critical is 100% read coverage. From the report from Walmart and all the adapters, no one can reach 100% read right now. Probably 99%, or someone even only get like 90%. So what happens if 1% is still missing? So when we have any technologies, what we can improve that to get 100% read. Also, there's an issue is people hope to get similar read performance in worldwide frequency, because in the worldwide, the frequency is very different, from 860 megahertz to 960 megahertz. But different countries use different frequencies. But the tag is already there. The tag will move around the world. It will be read in different frequencies. Because of the RF properties of these tags, the read performance in different frequencies will be different. But people want that it should be almost a similar performance around the world. And the another thing is the security and authentication. Just the previous speakers from the web, they're all talking about security issue. If there's no security, I think the RFID application will just get very limited. So just this ironically say that the hack, EPC hack, get attacked from, I think it's from 2 days ago. So people pretend to be hack members, and they post on the hack. So all the hack members got all these junk mails. So this is the issue: is when internet comes out, there's no security concerns. Internet comes from academics, so at first it's the DoD sponsored program, and then grow and grow. There's no one is planning all the security issues on the internet. Right now, the problems comes out. So right now we're talking about Internet of Things. So we need to really think about the security issues. So what we are doing right now, we are trying to improve the read range. Improve the read range is basically to reduce the power consumption of the tag chip. If it consumes less power, then the read range will be longer. So what we are doing is we try to improve the conversion efficiency for rectifier, because this is the RF signals coming from the reader and to the tag chip, and the tag chip will convert that into a DC power to power the chip. So if you can improve the conversion efficiency, then it's the read range will also be improved. And also there are some special technologies being studied to reduce the power consumption. For example, is we call substation digital circuits. If you have any background on digital circuits, you will know all the why we need a power supply to power the digital circuitry, because the digital circuitry is a need to switch. But there's a threshold to switch the circuit on and off. So there's a threshold. But if the threshold is lower, then the voltage applied to that will be lower. Right now, there's a circuitry which we do not use the regular on and off mechanism, but we use a circuit called sub-threshold. Even you apply a voltage which lower than the threshold, it still controls the circuit on and off. Then this will reduce the power consumption. And also there is a new circuitry called adiabatic circuitry. Although this circuitry type is a long time ago, but recently we find out this probably can be applied to the tag chip design. There's also some other conventional low power circuit design technologies there. This is what we've done recently. We recently published a paper here, on the, we improved the rectifier efficiency by about 30 to 100%. That means double the efficiency. Normally, the efficiency is around like 20, 30%, and we can improve it into 40 or 60%. Basically, we use a called bootstrapped rectifier to get rid of the VT drop of the circuitry. The second thing is we are working on is there's a circuitry called adiabatic circuitry, which means the charge in the circuitry can be recycled. But previously, some people already published the papers, they use this adiabatic circuitry, but they convert it normally an electronic system is powered by a DC power. So they convert the DC power to a power clock because adiabatic circuitry need a power clock. And then to power the adiabatic circuitry. But in RFID, because we got the power supply from the radio signal. So the radio signal is already powered clock. It's already clock. So we can directly use that as the power clock. So then we get rid of the rectifier circuitry. So which eliminates the loss of the energy. And also it's because the adiabatic circuitry consumes less power than normal logic, then the whole power consumption of the tag is getting reduced a lot. By doing this, we estimated that probably we can get only 10% of the power consumption as normal circuitry. So this means what we can do, we can increase the read range of the tag by a factor of 2 to 3. So another things I already talked about is called sub-threshold circuitry. This curve shows that the power consumption by different power supply voltage. If we use the supply voltage of, say, less than the threshold voltage of a transistor, we may get 4 orders of magnitude of reduction of power consumption. But this circuitry have the limit of the working frequency is very low. Probably only go to 1 meg. We got a simulation. So if we let the circuitry only work at 1 meg at 1 volt, the tag chip may only consume 10 nanoamp, which is only 1% of a normal power consumption of tag. By doing this, you see we may increase the read range by a factor of even 10. And also, we are trying to figure out what really prevents you read from 100% of the tag. So why these missing tag? The tag is missing. Recently, we find out a way that if you put 2 tags next to each other, one in closer to the reader, another one is behind that, and the one behind that will probably cannot be read. But if you remove the one in closer to the read, the one there can be read. So look like the one closer to the reader, get masked, the tags behind it. This is because the normal tag technology, they use a rectifier. Because when the tag is closer to the reader, it gets more energy. So the energy go into the tag need to go somewhere. So it has a circuitry that converts it just to heat. So it consumes high power when the tag close to the reader. So this, because the tag consumes the power, then the magnetic wave will just stop there, will not go further to the tag after that. So what we do, we are trying to have a new circuitry which detect whether the tag got enough power. If get enough power, it just try to detune the tune circuitry so that it does not consume energy. It only absorbs energy it needed. All the other energy is just let go away. So this can have this tag, behind that can get enough energy to get power. So this is we are doing. So what we are doing right now is, so we can detect the power supply of the tag and then compare to a reference, and then should try to tune the resonant capacitor of the antenna, and it just make it works. Okay. Also, for the worldwide frequency things, we also use this adaptive tuning ways. So it will detect the power. If get less power, it will try to tune the resonant cap to find a best point, which resonant at the frequency of the reader. So this make the performance get improved. Also, security and authentications is get considered. So there will be a two-way authentication is designed to both the reader, you authenticate the tags, and the reader tag get authentication from the readers. So, but this is really challenging because the tag is a so tiny chip and it consumes less power. So it needs low cost, low power. But it's also need adequate security between tag and readers. We have tried a way which we integrate some authentication into the Gen 2 protocol to try to have the tag and the readers get authentication. We have some first simulations down. It kind of looks like work, but we still need a lot of work to do. Okay, that's my presentation. Thank you.
And our next speaker is Sang-Gug Lee, who is an associate professor in the School of Engineering at the Auto ID Labs at ICU Korea.
In my talk, I would like to quickly go through the USN technology in Korea, and then we introduce what we are working on in Auto ID Lab Korea. What I mean by USN is a ubiquitous sensor network, which is known as a wireless sensor network. So the content would be some brief overview of what is going on inside Korea in this area, and then in relation to what's going on in Korea, what we're doing in Auto ID Lab Korea. Probably some of you are familiar with this 839. It's called the Information Technology 839 strategy that Korean government came up with. And there's 8 areas where we are trying to promote services, and then 3 infrastructures, and then 9 different areas of a growth engine that the Korean government is working on. And in these 839 strategy, you find that in the service area, the government is trying to provide RFID-based services. And then also in the infrastructure area, by utilizing the ubiquitous sensor network, the Korean government consider ubiquitous sensor network as one of the infrastructures that they would like to deploy in Korea, inside Korea. And then through that, hoping to be able to deploy these 9 different areas of growth engines. And for being more specific with the time schedule, each of these 9 areas, they have schedules, and then when they would like to, what kind of technology for the commercialization. And if you look at the pink colored icon there, this is the RFID and USN area where the government is trying to commercialize a mobile RFID by year 2006, which is before the end of this year, and then hoping to be able to deploy the sensor tag or sensor node technology for the public application. And the concept of a public ubiquitous sensor network is basically based on the broadband convergence network, all these services where the sensor network-based services would be available, such that everywhere, everything with RFID tags, and we sense the sensing IDs and environmental information, and then real-time monitoring and the control through the network would be available. That's the idea here. And the applications I'm sure most of you are already familiar with, they are smart buildings, factory automation and monitoring, asset monitoring and management, structural health monitoring, and environmental management. All this, we call this as a public ubiquitous sensor network technology. These are the targets the government is thrusting. And if you look at the technology tree, these are the infrastructures, sensor, starting the sensor, and then service available there. While I was watching this, this morning, I was getting this philosophical question. We talk about all these technology trying to make our life really easy and happy and all that. But I'm also at the same time finding out how all these technology try to actually make our life miserable. You realize what I mean, right? All these mobile phone technologies and internet, it seems like it's helping us in many different areas, but at the same time, we're finding out ourselves, running like crazy. It makes our life so busy. It does not really make our life happy. But I guess the race has started, and it's just an unstoppable race that everybody has to run all at the same time. But anyway, so these are what the government is trying to do, and this is their roadmap for actual, milestones and roadmaps and how they would like to establish these technologies and implement these technologies for the commercial applications. And in relation to that, what we try to do in Automotive Lab Korea is what I have just talked about is basically a public ubiquitous sensor network technology that they try to deploy. And in Automotive Lab Korea, here what we're trying to do is we try to make this public ubiquitous sensor network technology being connected to the EPC network. So the theme of technology thrust in Automotive Lab Korea is EPC network-based sensor network technology. That's what we're trying to go after. And we have 7 professors involved in this thrust, coming from the different backgrounds. And our focus area is hardware and communication technology for EPC-based next-generation ubiquitous sensor network, and some of the middleware technology for EPC sensor network, and then the privacy and security issues, as well as the business model developments for the EPC sensor network applications. And these are some of the research work that has been done as part of those thrust. And this is some hardware-oriented area where we've been working on the impulse radio development, which is being developed for the ranging and locationing. There's some typo there. We've been working on some pulse generator circuits, very low power pulse generator circuits on that, and then also very low power correlator circuits and stuff like that. But so basically we're working on transceiver designs, modems for some algorithms, and then MAC for ranging and locationing purposes. At the same time, we're also working on the reactive micro-radio technology, which means that the sensor responding to the signal. In other words, the sensor is under the sleep mode and respond only when it is being waked up by some wake-up signals, which is, I'm sure, a number of research institutes are working on at the moment. Also, this is some of the work that we're working on the sensor network middleware architecture, where the circled area, I think the whole block diagram represents the EPC network, and the circled part represents the area where, in order for this EPC network being connected to the public ubiquitous sensor network system. And we also, some progress is being made in the security and privacy area as well. And through all these activities, in other words, RF and chip sensor interfaces and networking and software, as well as business application, privacy and security issue, we're hoping that the research that we're doing would be related to the future standardization that connects the public ubiquitous sensor network with the EPC network. That's it.
Our next speaker and a member of the conference committee, Giselle Bennett from Georgia Tech.
All right, I am going to somewhat switch gears and go as quickly as I possibly can with the 10 minutes allocated with, I think, 30 some odd slides. And the whole point that I hope you walk away with is understanding the importance of requirements. We've talked about RFID, and we've talked about a number of applications, but understanding the requirements and what solution is going to meet your application is really critical. And we had a project that I'm going to focus on a container project, and looking at sensors that have built-in tags that have built-in sensors to monitor the environment, to monitor the condition of an asset. And so this is one of my favorite slides because I think it goes back to World War II, if I'm not mistaken. And you know, really, you're really trying to find something in all the things that we're talking about. RFID happens to be one mechanism. And of course, the big motivator was the Walmart and the DoD. And one of my sort of focus areas will be the DoD particular application. RFID is everywhere. Comes under different forms, different marketing, but everybody's pushing towards it. And really, as I indicated initially, asset tracking is really our focus. So if it's RFID, terrific. If it's some other mechanism, that's good too. Understanding the requirements is a really critical element to all of this. As you can see, and this is, I think, actually, I have to apologize, an old slide, because I'm sure the number of patents have actually increased beyond that in the RFID arena. I don't need to get into what automatic identification tracking is with this audience. We've got a number of elements. We've talked about them in some of the other talks. We're going to talk about them. They're going to come up in other discussions. But again, tracking something, storing information, and doing something with that data. All of these elements have come up in the talks. They're all critical elements, and they come in different shapes and forms. Biometrics is another technology that should be looked at for security, authenticity, and that's something that might be integrated in. Not RFID, but integrated within the RFID systems, if you will, and data gathering. Now, when I talk about requirements, this is one of my favorite slides, and I contribute this to Nick Tugas from the DoD IIT office. And understanding requirements is really critical. So Walmart has been the pin-up CPG that gets referenced as the start of all of the RFID flurry, and DoD followed suit soon thereafter. But DoD can't really apply a lot of the commercial applications because if they could, then their stores would move, Walmart stores would move every so often. Christmas would be a random event, maybe every 5 years, not once a year in December. The associates would be wearing different types of vests. And a stock out, it means something completely different for the DoD than it does for Walmart. So understanding those requirements and the environment you have to work in kind of changes what technology you're going to use and how you're going to apply that technology. The way we got into this, we were approached by the Navy to solve a problem of managing their high-value assets, and in particular the engines. The problem is they were improperly stored and improperly tracked. So when they were able to find an engine that they were looking for, they were supposed to be in pretty good condition. They'd find it floating in water, and thus what was a perfectly good engine now had to be sent back to the depot. So you can imagine the cost, the readiness issues, all of the implications. And that's assuming you found the container that had that engine. So with that, what we ended up doing is looking at an active RFID tag and looking at a tag that would tell you, that would monitor the container, which is the housing element for the asset that we were interested in. Not necessarily container, but it was the asset. And telling you where it was, what are the temperature conditions, what are the pressure conditions, was this container dropped, where has it been, and ultimately looking into, is it emitting a chemical when you get into homeland security issues? And so we developed a tag, looked at common standards, integrated those standards onto a tag. And when you hear the various talks, you're going to hear about a number of issues of power, range for RFID, durability. And so what we looked at, and some of the interesting things that capitalize actually from the computer science world, is how do we network these tags? If we want to keep the power low, that's going to have an implication about how much distance and range we get. Now, these are active tags. So with that, if we can implement kind of a hopping, and it's not really an ad hoc network to say, but it looks like it, where we can hop from tag to tag to tag to find the furthest tag away without increasing power, without changing anything else, then we can form this network and get a map of where all our assets are. And so that's what we ended up doing to get around the power issue. One of my last slides, I'll get into future technologies, and some of the things that we need to consider are power scavenging, ways to get power from other means, especially when you're dealing with active systems where the power is self-contained. You've got to look at that because that's one of the greatest technology hurdles. And nothing to do with RFID, but it's a technology that has lots of research areas. Contact memory buttons are something I pointed out early on. If you want to store asset information, maintenance history on an item, and be able to gather that without having to open up the container, find the paperwork, all of that can be integrated within. Earlier there was mention about an architecture. Not only do you have a hardware architecture, but an information architecture that you're dealing with. We had a pilot study, and everything you can think of that could go wrong went wrong, but finding power out in the field is a major issue. Having the ability to connect up to a computer without having to get lots of permissions was a major issue. In this particular case, luckily we didn't have any other RF interference conditions, but in a warehouse environment, what happened in an installation of an RFID system, it shut down the entire wireless network because they were incompatible. So a lot of things that you've got to look at. It's not just a slap and ship and it's going to work. In our active case, if we had a forklift or something come in between the containers and the tags, and read rate stopped. What we're seeing on commercial data is that you'll have an item that goes from the back stock to the store and then back again and back and forth. Well, that's not happening. The accuracy that was discussed earlier is another critical issue. What do you do with the data? Extremely important. And if you're not going to use the data, then why bother tagging your assets? And so that's another element that I think is now getting on the forefront. And there are a lot of other actually side benefits that came about for this particular project. They were using brand new containers that were unpressurized, and so just the testing of the containers and making sure they're protecting the assets in itself was a side benefit that came out of that project. So a lot of things to consider that we've talked about. Tag and label issue, these things are being discussed by various standards committees. Please follow those standards. The guidelines have been thought through very carefully. A lot of parameters. We talked about how far, how fast, how much data, how much content, memory. Security is another interesting component, and I never thought about somebody walking along the street with a reader and being able to decide which car they're going to break into based on the contents in the truck, in the trunk, until one of my students brought up that as an application or as a problem to solve. And so there are a lot of things. Privacy, of course, is another big one. And other considerations we'll get into in various talks on collisions. Lots of lessons learned, site surveys, power, the information system is very critical. And where I think some of the areas are, and we've discussed these earlier, include the various applications. The applications are endless. Nanotechnology, power sources, packaging, which will be a session tomorrow, how can we embed some of these things in the packaging that you're using to ship your assets? And the term that we're using of performance-based logistics or logistical prognostics, taking algorithms that we use for predicting failures in equipment and look at them for predicting failures in the logistics pipeline. These are all things to consider and take a look at, and lots of work, as Sanjay indicated, research areas.
And then Manfred Igny, who's the group coordinator for the VLSI and security group at PROACT at the University of TU Graz, that has a joint research project with Philips. And it's actually Henri Bartel, who's the head of EPC Global Europe, who suggested that we might want to consider some of the European experience with encryption in the smart card industry as it might relate to RFID.
Thank you. Thank you for the introduction. So it's a pleasure for me to present our results. We are involved in research for security, tag reader security on our RFID since, let's say, 2 or 3 years, involving from smart card implementations of crypto modules and this stuff. And yeah, I'm happy to show you our results. I will talk a little bit of our group, what we are doing, and tell you the requirements we define for our developments, and tell you the problems you face as a developer of crypto modules for tag application, and show you some of our results we achieved so far. So we are a group of about 50 people doing research on IT security, from development of crypto algorithms. Vincent Ryman, the inventor of the advanced encryption standard, is with us, up to e-government applications. And I am the group leader of the group that is doing VLSI, so hardware implementations for crypto. We are doing implementations for smart cards, for embedded systems, accelerator cards for encrypted networks and this stuff. We are also doing a lot of system and chip design. Our major activity at the moment is side channel analysis, which is a major topic in smart card industry. So there are attacks where you measure the current and try to get some secret about the key from the current measurements. This will also be a topic for RFID tags. And we are doing projects with quantum crypto groups. And yeah, this is what makes us so special, is probably the strong interaction with the other groups we have at our institute. Especially when developing AES modules, it was very helpful to have Vincent Ryman sitting with us together to find out how we can serialize the algorithm to comply with the requirements we have in RFID. So we talked a lot about that already. I will skip that slide because Sanjay today in the morning was all explaining this. So there is actually a need for security, and we say if you put security on a tag or on RFID, you should use proper security. So lightweight security in our sense is not lightweight crypto, so lightweight implementation of real crypto. Because if you try to get in with security in a globalized technology, you will need standardization, and that prevents, of course, secrets in the algorithm. So the standardized algorithms like AES, RSA, ECC, they are approved by experts. So there is some work spent in investigations if they are secure, and if you do not use them, you're probable to flaws in your systems. And the thing is, you should not only look at the algorithms you use. Most systems get broken because they do not use standardized protocols. So most flaws in systems are in protocols. And now I want to bring some arguments against and for standardized algorithms. So some people say that if you use standardized algorithms, they are easy to attack because there are so many publications on attacks. And then you do not take into account that your developers of the system, and if you're talking about RFID, there are a lot of developers, they are potentially attackers. I mean, the secret is not a secret if so many people get involved. And some people say that especially side channel analysis is more dangerous if the algorithms are known. And I mean, if the RFID tag are in the hand of the attackers, and they are in the hand of the attackers, I would apply a side channel attack. And if you understand side channel attacks, it's easy to adopt them to other algorithms. It's also easy to use them to find out about specifics of secret algorithms, so that's not a question. And some people say that custom-built algorithms use less secure, you lose less resources. And I say that they are potentially less secure. If you use them, things might happen like it was exactly last year, I think, this break of the John Hopkins guys of the speed bus. And we say that proper implementations of standardized algorithms are possible for passive devices for RFID tags, and I will show you later on our modules. So when we started, we defined some requirements for secure tags we wanted to develop, and we said right from the start, we do not want lightweight crypto, we want real crypto, like the same standard as in smart card industry. We wanted to use standardized algorithms because the high number of tags we will have is enough value. Then even if each tag just protects small value, it's a good point of attack for an attacker, because the high number of tags makes a hack very interesting. But the high number of tag logically needs a very clever key management. So we do not have systems like that so far. We didn't want to accept a raise of costs, a significant raise of costs due to our security implementations we wanted to have on the tags. And we didn't want to accept a reduction in reading distance. So we had to comply with this very small power consumption. And we wanted to be compatible with already installed infrastructure. So we didn't want to suggest a system which is never accepted because there are so many readers already out there. And there we started, and then we were facing a lot of limitations due to the technology. So the main problem is the power consumption. So if we do not accept reduction in the reading distance, we were facing that we have about 10 microamps available. The area consumption, which is less problem with newer semiconductor technology, but it's still the technology that's now available. We have very limited execution time, in fact, because, well, we have a rather limited clock frequency. So the protocols, that was actually a problem, because in other things you can say, a client and a server client just don't respond or something like that. But here, always the protocol is always initiated by the reader, and that's different. So, and there is no physical protection possible. And then there were a lot of publications in the last year where people state that hash is more inexpensive than encryption, and just simply not true. So I do not say that this research is useless, but they should use encryption modules instead of hash modules, because they are easier to implement in hardware. So what are the enhancements we want to propose? For tag authentication, we will need then extended personalization. We will need a crypto primitive on a tag, and we will need a secure key storage on a tag, which is a problem that is not treated so far. And we need a crypto capability of the reader or a secure access to a verification server. For reader authentication, we will need one additional thing. That's a nonce generation. Nonce is a number used once. It's kind of pseudo-random number. It has to be fresh and unpredictable, and that's not an easy task for RFID tags. What are the results so far in our institute? We developed an AES module which complies with the requirements for tags. So it uses 4.5 microwatts. That's produced, that's verified, that's available. The only thing is there is no countermeasures against side channel attacks on this module. That's what we are working on so far. We presented security layers for ISO 18000. The reason why we chosen this standard is because we were used to the ISO standards from smart card, And it was when we started clearer to us the concept of defining new commons, like these custom commons, which were foreseen in ISO 18000. In fact, it doesn't make a big difference if we use EPC or ISO. We have protocol security layers for anti-cloning, for privacy enhancement, and this is tested with an tag emulator on an FPGA basis. And we have asymmetric crypto modules using elliptic curve cryptography, which are usable on passive devices. So what are our future tasks? We should work actually on key management and personalization, on testability of crypto tags. Nobody mentioned that so far. This will be a problem in future. So if there is more functionality on tags, how will you test them? Compliance testing is already a topic, but this will be a more interesting topic. We have to deal with this nonce generation on tag and further research on asymmetric crypto. So what are the conclusions? Use standardized crypto if you state that you will design secure RFID systems, because you never know what your system is used for then. The protection will be also necessary on inexpensive tags in future, because you never know the applications. Also protection against side channel analysis. And, well, according to our results so far, I would say the implementation of standardized crypto is possible on passive devices if you go for a clever implementation. And more research is definitely necessary for integration into running applications, to future applications. This is a list of our recent papers, and I just want to mention our initiative PROACT. We are looking for research for professorship and for visiting professors and stronger interaction with the RFID community in the next years. And thank you.
Any questions for this distinguished panel around just the tags and the future of tags? If we could ask you to come down to the mics.
This is Chris Flöckmeyer from the Automotive lab in Switzerland. I have just a quick question regarding your work on power consumption reduction. If you look at the work, say, of Karthaus from Atmel on transponders, their transponders needed about 16 microwatts at the antenna and probably about 4 microwatts on the chip before the rectifier. Where do you think your work will take this? Do you think you can go significantly beyond 1 microwatt for power consumption of a tag for read access?
Actually, your question is, you will see that the minimum power for the tag, there's IF power, say it's like 16 microwatt, but the real digital power consumption is like a 4 watt. So this means like there's only 20% of the microwave power is converted into DC power. So our work is we can get the performance better by doing two things. One is we can improve the conversion rate, which is we can higher efficiency to convert the microwave power into DC power. The second thing is by carefully designing the digital circuitry will reduce the power consumption. So this is a two-way we should go do together to reduce the whole power consumption. But eventually, what decide the read range is the IF power, decide the whole read range.
But where do you think this is moving to? I mean, do you see that at some point we will be down to like 1 microwatts?
I think probably even less than 1 microwatts. Yeah, it's, just like in my presentation, so if we use some special circuitry, we even can reduce the power consumption by a factor of 10, even 100. We take advantage of that the tag really work in really low operating speed. So for the maximum the clock in a Gen 2, it's only 640K, so which is much, even 1,000 times slower than a PC is working. So probably it's just can, use some special circuitry, you can reduce the power of that to like 100 times, then, less than 1 microwatts.
Okay, thanks very much.
Okay.
So So thank you very much. If we could ask the next panel to come up in the interest of time.